second.
Or did we do? No, we didn't. Yeah, we did those.
Yeah. Well, let's do 13, 14, and 15 for sure.
Okay.
Even if it's review, it's not a bad
Yeah.
thing.
Not at all.
On a moment.
More practice.
Snap left and snap right.
Cool.
And blow it up a little bit. Oddly enough, I discovered something in working with another student today. When you draw a quadrilateral inscribed in a circle, like 13 is, the opposite angles are supplementary. I didn't know that.
Yeah.
In other words, the way I would have solved question 13 would be
180 minus that number divided by 2, right?
Chosen one of the angles and figured out the arc length measurement. Not the arc length, but the measurement of the arc. And once you figure out, in other words, if you choose the 80-degree angle, and that's the equivalent of the arc QRS, so that has to be 160 degrees,
right?
Which makes the arc QTS be 200, and then you can figure out what x is. X is 100. And once you figure out x, you can figure out y, but doing it that way is one way, but I never realized that the opposite angles are supplementary when you inscribe a quadrilateral inside of a circle. So we could have done it immediately by just saying x was 100 and y was 85. In other words, the opposite angles have to be supplementary, and I didn't know that, which means you can do 14 easier. M has to be 120.
It does. Yeah.
F has to be 120, which means K is 60. So you could do these instantly, which I didn't do when I went through them with you.
Oh, that's all right. Yeah.
Well, it's just an interesting additional piece of information. It doesn't, in other words, if you look at both of those questions, it looks like you have to do them the way questions 1 through 12 were done, which is to figure out the measurement of the arc length and then go from there. But not true. The 13, 14, and 15 are actually the easiest problems on the page.
Yeah, for sure.
Now, 15 is a little different. Did we do 15?
I believe we did, yeah.
Okay, well I have another page we can look at. But 15, we don't have any opposite angles. In other words, K is opposite L, but they don't tell us what L is.
No.
So the only way to do 15 is to figure out the measurement of JK. And we can do that because it's the only arc not defined. So all 4 arc measurements have to total 360.
Right.
So that makes JK 66. And once you know what JK is, then you can figure out that 3A subtends MJK, and you can figure out what 3A is. And the same with B. So it's a little different. It is, It's most likely the hardest problem on the page for sure.
Hands down, yeah.
Go to the next page. Since we did that whole page.
Cool.
Let's look at number 16. And let me draw 16 because it's not immediately obvious how to solve it.
Yeah.
I'm getting better and better at drawing circles.
that looks good.
That is a good circle, isn't it?
It is.
I mean, considering I can barely draw a straight line,
That was
for
awesome.
some reason I can draw circles, and I don't know why. All right, so that's B, A, C, and D. And what they tell us is that ADC is 60 degrees.
Mm-hmm.
Can you figure out what ABC is?
Yeah, you can.
In other
Yeah.
words, that angle right there, X, what is it?
120. Well, actually, no. How would you do that? So you
Well, you're
do,
close. You're not
so you
that
do
far off. You
180 minus.
multiplied by 2 instead of dividing by 2.
Okay.
Always remember that when you're dealing with these circle problems, either, in other words, this is a central angle.
Mm-hmm.
The vertex is at the center of the circle.
Right.
That makes that arc 60 degrees from A to C.
Right.
Central angles always subtend an arc that's the same measurement. But notice that angle B also subtends that same arc.
Mm-hmm.
The only difference is that angle B's vertex is on the circumference. It's not a central angle.
Right.
So what does X have to be?
So X would have to be, well, you just divide by 2 then, so it'd just be
Exactly.
30, right?
Exactly.
Yeah.
In other words, 2 is the magic number in all of these things.
Yeah,
Either
you
you're
either multiply or
multiplying by 2 or you're dividing by 2.
Right.
Okay? But the fact of the matter is that angle B subtends the same arc, AC.
Right.
And the measurement of the angle is always half of the
Mm-hmm.
arc measurement that it subtends.
Yeah.
Now, I asked a student earlier today, are you familiar with the word subtend? Is that one your geometry teacher uses?
He doesn't use it, no. But I've
Probably
heard it
uses
before.
the terminology shares with.
Probably, yeah. I've heard him say that a couple times.
Because my other student was not familiar with the terminology subtend. But
Right.
subtend basically means, and it doesn't matter, in other words, if I have that,
Mm-hmm.
then angle theta subtends the arc from A to B.
Mm-hmm.
Also, if I were to draw it like this, then angle C also subtends that same arc.
AB. Yeah.
Okay? So AB is going to be theta because it's the same as the angle that comes from the central angle.
Right.
But angle C is going to be 1/2 theta.
Yeah.
And you can always see that by just drawing an example. If you ever forget which one is equal and which one is times 2, well, just draw a picture and it's clear that that angle is bigger than that angle. And it looks like it's about double. So 2 is the magic number.
Mm-hmm.
Okay?
Okay. Cool.
So, and that applies to a lot of geometry. When I'm figuring the area of a trapezoid,
Mm-hmm.
it's not base times height because there's 2 different bases.
Right. It's base 1 times base height divided by 2.
Base 1 plus base 2 divided by 2, that's the average base.
Right.
And the average base would be like that. So it's the average base times the height. But this number 2 comes into a lot of geometry.
Yeah,
And
for sure.
you can always figure it out just by drawing a picture of it. In other words, it wouldn't make any sense to just do base 1 plus base 2 times height, because a rectangle is base times height. So this has to be average base, and you get the average base by adding the two bases and dividing by 2.
Exactly. Yeah.
All right, let's look at 17.
Cool.
Every angle is the same in this pentagram. You can draw a pentagram by basically doing this.
That was a perfect circle as well.
I don't know why. I can draw circles better than straight lines. If I try to draw a straight line, I'm lucky if I can make it even close to straight. But circles, for some reason, I can draw. I don't know.
Yeah.
It's odd. All right. Let's look at this problem. In other words, they want to know that what they're saying is that all of those angles are the same.
Yeah.
And they want to know what one of them is.
Okay.
Okay. So let's look at this problem in the same way we've done every other problem in this section. Which is, let's examine the arc length, not the arc lengths, the measurement of the arcs.
Okay. For these, could you just see 360 divided by how many triangles there are? Or like 360 divided by 5 since there are 5?
Well, it's not obvious that that's the way to do it.
Yeah.
Let's examine it by looking at one of the thetas.
Okay.
One of the thetas subtends that arc, correct?
Yeah.
The second theta, that's this one here. The second theta subtends this arc. The third theta subtends this arc. The fourth theta subtends that arc, and the fifth theta subtends that arc. So all of the arc lengths, or the measurement of the arcs, is what?
So since they subtend each other,
Well, not each other.
Just 45.
One goes from there to there, the other goes from there to there, the other goes from there to there, the other goes from there to there. What's the sum of all those arc lengths?
360.
Yeah. So all of the arc lengths are 360, or measurements of arcs.
Right.
And what do we know about the angles? In other words, if I want to know what that is right there, what is theta?
Theta is 90 degrees, right?
Well, theta is half of x.
Oh, okay.
Right? In other words, every other problem we had here, when you had an angle, it was half of the measurement of the arc.
Right.
So if I know that all 5 thetas subtend exactly 360 degrees, then each theta has to subtend 1/2 or 1/5. There's 5 thetas. So if I divide that by 5, 1 is 72 degrees. In other words, that's 72 degrees, that's 72 degrees, that's 72 degrees, that's 72 degrees, and that's 72 degrees. And that adds to 360, and that takes care of every single measurement of arc.
Cool. So yeah, you could just do the same for B and C then.
So what is theta? If each of these arc lengths is 72, what's theta?
Half of x.
36.
So 36. Cool.
So, and each one of these problems is the same. In other words, if you look at each theta in B, they each subtend an arc, and all of those arcs make up the full circle. Nothing extra, nothing less. There's no overlap, every single angle subtends an arc, and if you add up all the arcs, you get 360. So in
Cool.
B, there are 7 thetas.
Mm-hmm.
So what is the measurement from that point to that point?
So from that point to that point would be, well,
There's
you
a
just,
total of 7 of them.
so 360 divided by 7, which is 51.4.
No, you're right. You're right. I did the math.
Is it? Yeah, there we go.
So what's each theta?
Half of that, so 51.4 divided by 2. 25.7, yeah.
That's the measurement of each angle.
Cool.
And it doesn't matter how many stars or how many points on the star you draw, every one of these is the same. In that
Right.
each angle subtends a arc measurement, and if you add up all of the arc measurements, they make up exactly 360. So if I have a 9-sided star, or 8, or whatever it is, I can figure out each arc measurement. And then you know that the angle that subtends that arc is always half. So that's the way to do those 3.
Cool.
Take a look at 18.
Okay.
What equation can I write for 18? Based on the picture.
Yeah. Does that say 8x plus 10?
It does. Here, let me,
Okay.
I can
So,
blow it up a little bit.
Sure. So you could do 8x plus 10 is equal to 12x plus 40.
Well, hold on a second. I like the way you started. Start on the left. Is it equal to the measurement of the arc, or is it equal to half the measurement of the arc?
It's equal to half of the measurement of the arc.
So let's write it that way. It's half of 12x plus 40.
Or could you just write it like 6x plus 20?
Well, I think it's very important to write it like this.
Right.
Because the overriding principle that we're dealing with in every one of these problems, and I mean every one of them, is that this angle is half the measurement of that arc.
Right.
So let's not do 2 steps in one.
Okay.
Do 1 step only.
Okay.
The first step is to write that that angle is half the measurement of that arc. And now we can solve it. Now we have an equation. Now it's an algebra problem. It's no longer a geometry problem.
Right.
So let's do a little algebra.
Okay.
What's the next?
So the next line would be 8x plus 10 is equal to 6x plus 40 or plus 20.
Next line.
And then we could subtract 6 from both sides. 6x.
Okay.
So you get 2x plus 10 is equal to 20. And then you get 2x is equal to 10, x is equal to 5.
Good. Very good. I like how fast you did that.
Awesome.
It's good algebra skills.
Thank you. Cool.
I'm looking at number 19.
Okay.
And I do not have a clue as to how they expect us to... it's a parallelogram.
Another perfect circle too, man.
Well, not just any old quadrilateral, it's a parallelogram.
Yeah.
Parallelograms have to look a certain way. They have to have both lines, both sides parallel to one another. And
Right.
notice that I had difficulty drawing it. But we do know, and we're going to label this Q, R, S, T, and it wants to know that angle. Cannot determine that angle.
Yeah.
I don't think We know that that angle x is the same as that angle x.
Mm-hmm.
Well, and we do know some other things. What's angle Q?
Oh, we know that Q is... Well, we know Q.
What's the relationship between adjacent angles in a parallelogram?
They're supplementary to each other.
So what is Q?
So Q would be...
This is x. Q is 180 minus x.
Right.
And if Q is 180 minus x, so is S.
Exactly.
Now, what can I say? What equation can I write?
Oh, we could do...
We have a quadrilateral. What do you know about the sum of the angles of a quadrilateral?
It has to add up to 360.
Okay?
So we can do
2x
180. Yeah.
plus 2 times 180 minus x
is equal to 360.
Ooh. Don't like where this is headed.
Yeah.
Notice where...
It's going to be a big number.
Well, notice where it's headed. No? Watch what happens.
Okay. Yeah.
Now the two x's cancel and I end up at 360 equals 360.
Right.
So I can't solve for x.
No.
And yet that's what it's asking us to do.
Yeah.
Let me think for a moment here.
Sure.
Let me just draw a parallelogram.
Okay.
I'm trying to figure out why it was so hard to draw a circle around a parallelogram.
Yeah.
Well, it has to connect there. It's not easy to draw a circle around a parallelogram, notice.
No.
It's not a very good circle. If I start with a good circle, why is it that I can draw a good circle? That baffles me. It does.
That's a perfect circle.
I can't draw anything because my hands shake too much or something.
Yeah, I can't.
Not easy to draw a parallelogram inscribed in a circle. So there must be something special about this problem that I'm missing. Examine it from the perspective of arc lengths, which I didn't do the first time we looked at it.
Yeah.
Hold on.
Sure.
So if that's angle x, the arc that it subtends is QTS, which would have to be 2x.
Right.
From there to there is 2x. And the arc that Q subtends would be from R to T, and that would be, wow, I'm not sure I know how to do this problem.
Me neither. I'm baffled.
Find the measurement of angle R. And it could be, first of all, it could be acute. It doesn't have to be the obtuse angle, so how can they ask us what it is? In other words, why couldn't I have drawn it just like this? In other words, the way I drew it, it was obtuse, but couldn't I have drawn it like this? So that it's the acute angle? So how can we possibly figure it out?
I don't know.
If it could be obtuse or if it could be acute,
Mm-hmm.
there must not be very many parallelograms that you can inscribe in a circle. Let's examine.
No.
In other words, the fact that I had so much trouble drawing it, maybe there's only one kind of parallelogram that you can draw in a circle.
Mm-hmm.
What would it be? Let's examine the diameter.
Okay.
In other words, maybe the parallelogram
Mm-hmm.
has to be drawn about that diameter.
Right.
And it's true, the diagonal
Mm-hmm.
is going to be the diameter of that circle.
Right.
Ah, that tells us a lot. If the diagonal of that parallelogram has to be the diameter of the circle,
Mm-hmm.
what is the measurement of that arc?
The diameter of that arc.
If that is a diameter of the circle, what is the
just be
measurement
180,
of that
right?
arc? 180, right?
Yeah, because it's just half of 360.
Okay, notice that that is the arc that is subtended by angle x.
Yeah.
So what is angle x?
Then angle x would have to be 90, right?
Yeah. So that's the answer.
Yeah.
And the problem is that the only parallelogram you can inscribe in a circle has to be a rectangle.
Right.
You cannot put a parallelogram in a circle that is not a rectangle.
You can't, no.
Oh, I didn't know that.
Mm-hmm.
And
Another good
as long
circle.
as it's a rectangle,
Mm-hmm.
then the diagonal of the rectangle is going to be the diameter of the circle,
Mm-hmm.
which makes that 90 degrees. And of course, if that's 90, that's 90. And if that's 90, both of these are 90. So it's
Right.
a rectangle. It's not just a parallelogram.
Mm-mm.
And that's what I just found, I just discovered today, is that you cannot put a parallelogram that's not a rectangle inscribed in a circle. No wonder I had so much trouble drawing it.
Right.
Because I was trying to draw a parallelogram, and usually when I draw parallelograms, I try to exaggerate it to make sure that it doesn't look like a rectangle.
Right.
But notice that when I draw this parallelogram, the only circle that fits
Mm-hmm.
is one whose diagonal of the parallelogram is the diameter of the circle. And then these 2 points don't touch the edge of the circle. So you cannot put a slanted parallelogram inside of a circle. You can't describe it unless it's a rectangle, in which every angle is 90 degrees.
Yeah.
So that's the answer to that one. That's actually a really good question.
That is a good question.
And that leads to the next 5.
Cool.
Can you put a square in a circle?
You can.
Yeah. That's a square is a rectangle, so as long as the angles are 90 degrees, you can do it.
Exactly.
Can you put a rectangle in there?
Yeah, definitely.
Can you put a parallelogram? You can, as long as it's a parallelogram with 90-degree angles.
Exactly. It can't be more.
Now, let's examine whether we can put a kite in there.
I doubt we can.
I don't know, to be honest.
Yeah.
Let's draw a circle.
Mm-hmm.
How is that possible?
That's a perfect.
How is that possible? I mean, to tell you, if I try to draw a straight line, that's the best I can possibly do. That's not bad.
That's pretty good too. Yeah.
But I can't always do that. A lot of times my straight lines end up looking like that, you know. So the fact that I can draw a circle amazes me. like one of those autistic skills. No, I can't add 2 plus 2, but I can do calculus.
Oh, exactly.
So a kite. A kite would look, well, that's one point of the kite. That's the other point of the kite. There's what we know about a kite is this. It looks absolutely like I can put a kite in there. I didn't have any trouble drawing it.
Right.
And that would be the diameter of the circle as well as the long diagonal of the kite.
So it will work.
I think it will, yeah. And in other words, well, let's do a little bit more rigorous test here.
Sure.
Trying to think of how, what does this angle here have to be?
That would have to be 45 degrees.
No. Think of the arc that it subtends.
Right, 90 degrees.
Right, because it subtends a 180 degree arc.
Yeah, exactly.
So if the kite is made up of 90 degrees there, which means 90 degrees over here, then you can do it.
Yeah, definitely.
Yeah, it doesn't make these angles 90 degrees.
No.
But as long as that's 90, then the main diagonal of the kite is going to be the diameter of the circle, and it'll work. In other words, it doesn't matter how I draw the circle. I can draw the kite as long as I draw those 2 points. And notice that I can put that angle. Anytime you draw a triangle in a semicircle like that, that is a right angle, no matter how I draw it.
Okay.
Okay? In other words, that's good to know. In other words, if I take a circle here and have a diameter, even if I draw the triangle like that, that has to be 90.
Yeah.
Or if I draw it like this, that has to be 90.
Right.
So if you inscribe a triangle in a semicircle, it has to be a right triangle.
Yeah.
Well, if you put 2 right triangles in a circle, you get a kite. That's what a kite, well, a kite doesn't have to have this be a right angle, but it certainly can be. In other words, if I put 2 right triangles back to back, I get a kite.
Yeah.
And so I can certainly do a kite.
Cool.
What else did it want to know?
Rhombus?
A rhombus. Well, a rhombus can be a square, right?
Right.
In other words, what's the primary definition of a rhombus?
4 sides that are 90 degrees.
No, you're close.
Two sides.
4 equal sides.
Okay.
That's all a rhombus needs. In other words, this is a rhombus. It's a parallelogram, but that side's equal to that side's equal to that, equal to that.
Right.
That's what makes it a rhombus. Now, I cannot inscribe that particular rhombus in a circle because, for one thing, the circle's diameter would have to be that.
Right.
And that is a longer diagonal than that is. So it's impossible to draw a circle that has that on the edge of the circle and that, because that line is not as long as the diameter of the circle. There's no way it's touching the edges of the circle.
Yeah.
So that kind of a parallelogram or rhombus, I could not draw in a circle. But we've already figured out that I can put any figure that has 90-degree angles in a circle. So I could certainly put a square in a circle.
Yeah.
Because that's a 90-degree angle. And that diagonal is equal to that diagonal, and both of those diagonals are equal to the diameter of the circle.
Exactly.
So you could put a rhombus in there as long as it has 90-degree angles. In other words, a square. You can put a square in a circle, but you cannot put any other kind of a rhombus. Any other rhombus that didn't have 90-degree angles is going to have different length diagonals, and therefore it won't inscribe in a circle.
Yeah, exactly.
Now let's talk about an isosceles trapezoid.
Okay.
Well, an isosceles trapezoid, by definition, has two sides that are the same and not parallel. Well, that was pretty easy to draw.
Yeah, definitely.
So I think I probably can put an isosceles trapezoid in a circle, but let's try to explain why. The explanation for all of these actually has to do with the measurement of the arc length that is subtended. In other words, this angle x subtends that arc length, right?
Yeah.
And this angle y subtends that arc length. Well, those two arc lengths make up the circle. So those two arc lengths, I keep saying arc length, I don't mean arc length, I mean measurement of the arc.
Oh, you're good.
In case you're wondering what the difference is, that's 180 degrees.
Yeah.
As a measurement of an arc. A semicircle is 180 degrees. But if that was a piece of string and I straightened it out, that would be the arc length. So there's definitely a difference between the terminology arc length and measurement of the arc. The measurement of the arc is in degrees. The arc length is in inches or meters or whatever. In other words, when you're talking circumference of a circle, you're talking arc length. If you took the entire circle and cut it and straightened it out, that would be the measurement, or that would be the length of the circumference. Whereas the arc, the measurement of the arc is in degrees, not in inches. So there's a considerable difference. But back to this trapezoid. One thing we know about a trapezoid is that if it's an isosceles trapezoid, that angle is also y.
Right.
And that angle is also x.
Just the opposite from each other.
Notice that x subtends this arc, y subtends the rest of it. So the sum of the two arcs is 360 degrees. So the sum of x plus y has to be 180.
Yeah.
Half of that.
Yeah.
So I could put an isosceles trapezoid inside that circle. As long as x plus y equals 180 degrees, and we know that's true with an isosceles trapezoid, is that the opposite angles are supplementary.
Yeah.
And the adjacent angles are supplementary. Yeah, no, I said that right. X plus y is equal to 180, and x plus y is equal to 180. So the adjacent angles are supplementary, and the opposite angles are supplementary in an isosceles trapezoid. And the fact that that's true means you can fit it inside of a circle. All right. Let's look at this last question. Let's see if we can get through this page here. in the diagram to the right, angle C is a right angle. If you draw the smallest possible circle through C and tangent to AB, the circle will, well, let's try doing what they're suggesting. First of all, let's draw that triangle.
Okay.
We know that's a right triangle because it's a 3, 4, 5.
Right.
You cannot have a 3, 4, 5 triangle without that being a right triangle. In other words, the Pythagorean theorem holds 3 squared plus 4 squared has to be equal to 5 squared.
Right.
And if 3 squared plus 4 squared is equal to 5 squared, this has to be a right angle. In other words, both statements are true.
Right.
Okay. Now, their question is that if I draw the smallest possible circle through C and tangent to AB, well, what they're talking about is a circle like the following. In other words, through C and tangent to AB. That's the kind of circle. In other words, it's not inscribed, it's not circumscribed.
Yeah.
It's a combination of both. And the circle will intersect AC at J. So that's J right there.
Yeah.
And BC at K, so that's K. Find the exact length of JK. Well, look at that picture. I've created a second triangle, right?
Yeah.
Which is also a right triangle. So what does JK have to be with regards to the circle?
180, because it's half.
Has to be the diameter.
Yeah.
In other words, remember that if I have half a circle and I draw a triangle in that half circle, that is always a right angle.
Yeah.
Which means if I have a right angle, a right triangle inside of a circle, that's always the diameter. So JK is the diameter, and they want us to find the exact length of that diameter. Wow.
Yeah. These are complicated.
Huh. Think about this for a minute. Definitely
Yeah, go ahead.
challenge.
Yeah.
So if I'm examining just this part of the circle. What can I figure out? Do I know the radius of that circle? No, I don't think so.
No.
I don't know the length of JC. I don't know the length of KC. Is all I know is that that is the diameter of the circle.
Yeah.
What else is the diameter of the circle?
That way. Yeah.
Height of that triangle. So that's going to be our answer. Let's draw that triangle separately. We're going to make it a 3, 4, 5. And we know that that height, what's the area of that triangle?
3 squared plus 4 squared is equal to 5 squared. So
what's the area? The area of a triangle is what? 1/2 base times height.
Right. So it'd be 15 or...
No, that's the base the way I've drawn it. But if we look at it differently, that's the base and that's the height.
So 6 would be the...
Yeah, so the area is 6.
Yeah.
Now, if we look at the triangle the way I've drawn it, the area is still 6, right?
Mm-hmm. Yeah.
But the area is now 1/2 the base times the height. Well, if I'm trying to solve for h, that means 6, the area, is equal to 1/2 5 times h.
Okay.
So h is going to be 12 divided by 5.
Uh-huh.
That is the answer to the diameter of that circle.
Right.
All diameters of the same circle are the same. So if it's 12/5 from there to there, then it has to be 12/5 from J to K.
Right.
Now the only thing I really didn't prove is that this vertical line is the diameter of the circle. Yes, I did prove it. Yes, I did prove it, because it's tangent at this point and it's tangent down here, and we know that any line that's drawn tangent is perpendicular to the tangent line, which makes it the diameter of that circle.
Yeah.
Once we determine that, we can figure out what its measurement is. This is a very clever problem because we know the area of that triangle because that's 3 is the base and 4 is the height, because that's a right angle. But if we draw it slightly differently, then 5 is the base and h is the height. But the one thing we know is the area of the triangle is the same regardless of how I draw it.
Right.
And so the area of the triangle is always 6, which is 1/2 the base times h, which we're trying to solve for. So I love this problem. That is
cool.
That is a great problem, and I'm not sure I would always be able to figure it out. I just happened to see it tonight.
Definitely.
So that's definitely a challenge problem.
For sure.
All right, Dylan, I will let you go.
Sounds good.
But it sounds like you're on top of these circle questions. It's funny, I had a student earlier that has struggled with geometry, but is really good on these circle.
That's exactly me,
Yeah, it is.
Yeah.
Exactly.
Algebra, algebra is my strong suit. Like, I can crank out algebra. It's just...
Well, I'm still not sure I get it.
Not...
I don't get what is different about these circle problems. The circle problems don't always turn into easy algebra problems.
No, they're difficult.
Definitely geometry problems.
Yeah, for sure.
So I'm not sure I understand what's going on, but I'm glad you get these so well.
Yeah, me too.
Yeah, that's terrific.
Awesome.
All right.
All right.
Have a good weekend. If you have any games this week,
thank you.
Good luck on them. And
oh, thank you. Appreciate it.
I'll talk to you next time.
Sounds good. Thank you, Mr. Cowan.
Bye-bye.